Good afternoon. This is the third session on properties of a pure substance, and we continue from where we left off yesterday, which was we were looking at the properties and I started discussing what is an ideal gas. So we had looked at the properties of vapors, and we said that the equation of state, which we are so familiar with, PV equal to RT, this doesn't apply to the vapor states, and this applies only to an ideal gas. And this is the simplest form of the equation of state. We call it, let's say, EOS, where we have P is equal to RT upon V. So basically, we have expressed pressure as a function of, say, specific volume and temperature, or rho and temperature. The reason for putting this form up is that we'll see in a minute that as we start deviating from ideal gas behavior, this equation will get modified. And essentially, it will remain something like this, but with lot more additions and modifications to make it fit the experimental data much better. So we will come across many different types of equations of states, and each one of them has their own advantages and disadvantages. But remember that all these are for an ideal gas only. So last time what we had seen is that we had defined the reduced temperature TR, T upon T critical, and we defined reduced pressure as the pressure upon the critical pressure. The reason we did that is that it gave us a uniform set of parameters that are independent of the material, and so in some way these reduced properties, these are some sort of a what we call a normalized on a known constant, and we can then talk in terms of different materials having same reduced temperatures behaving in a similar way. So we define these two, and turns out that these are the critical states are the properties of the substance, and along with that we have other critical states like the critical state specific volume, the specific entropy, the specific enthalpy, specific internal energy, and so on. For a given substance, all these are unique, and you can just look up any tables and we can pick up all these numbers from there. So this is what we defined, and then we went about doing an exercise of saying that if we plot this side the reduced pressure and this side the y-axis, we plot the compressibility factor, then what will the graphs look like? For that we defined yesterday the compressibility factor Z as PV actual divided by RT, or is a ratio of the actual specific volume of the material divided by the specific volume that would be calculated from the ideal gas equations. What basically we are saying though is that when we talk of V ideal gas equation of state, this lower part, if you have any pressure, any temperature for a material, nothing stops us from saying that I will calculate V as RT upon P. But the question is, this is from the ideal gas assumption, and the question is, how good is this assumption? And that is what if this ratio tells us, that we measure something in the laboratory divided by what the ideal gas equation of state tells us, and we get the compressibility factor Z. And we went about drawing this curve and saying that ideally if Z is equal to 1 and this is 1.0, this is 0, and this is a logarithmic scale going from 0.01 reduced pressure to say 0.1, 1 and say 10, and even further than to 100. And we argued yesterday that at very low pressures, when we start plotting, we say, well, at a certain reduced temperature, what is the Z? We start getting one problem. We say, well, okay, now at this reduced pressure and under the same reduced temperature, what do I get? That's the point. At this and the same reduced temperature, we get this. So like that, if we go about doing plots, we'll get a series of points. They start looking something like this. This would be at some particular value of reduced temperature. At some other value of reduced temperature, it begins to look like that. In some cases, it goes like that and then goes up. So around here, not at 1, but something like more than 10, we see that Z becomes much greater than 1. Whereas on this side, Z is less than 1. That means as pressures remain low and temperatures keep increasing, the strength of Z, which is divergence from ideal gas behavior, increases, and Z more than 1 means that V actual is greater than V ideal gas. This is when Z is greater than 1. If Z is less than 1, it means that this is less than this. So V actual is less than what V ideal gas. That means actually the material, the density would be the opposite. So you can look at it that way, that here density is less than the ideal gas prediction, and here it is opposite. So in one case the molecules are actually closer than what ideal gas predicts. In the other case, they are further apart than what the ideal gas equation predicts. That's what these two are telling us. This complicates life quite a bit. Because what has happened now is that the nice equation of state that we had, PV equal to RT, has now to be changed, and we have to modify this as P is equal to Z times RT upon V. And Z, as you can see here, this is a function of reduced pressure and reduced temperature. Or for a substance, it is a function of pressure and temperature. If you take reduced pressure and reduced temperature, you get a common graph which I will show you in a minute. So how do we get this? And that equation for Z, this is what, again, one has to do curve fitting, and it comes out with a big long equation. Okay, so before that, let's look at how this curve actually looks like. Okay, so this is the real graph with real data from substances, and here is what you see on this picture. In the legend, it says there is data for methane, ethylene, ethane, propane, butane, isopentane, N-heptane, nitrogen, carbon dioxide, and water. So we took the real data, measurements, calculated Z, and plotted these. And you can see, so let's take the first curve at the top here, this one, and you can see that there are some points that are there. There are these circles which are there, triangles which are there, some crosses which are there, and then they all fall within a relatively narrow band through which a curve fit has been done. The same thing was done with reduced temperature of 1.3, and we get this sort of a fit, and at reduced temperature of 1, that means temperature is equal to critical temperature. We get all these points here and then they go off here, they all fall on one line. And this axis for reduced pressure is a linear axis and Z is also a linear axis. And the maximum here is reduced temperature of 2, which means we are twice greater than the critical temperature. So this is the reason why the generalized compressibility chart, as this is known, is so nice. That irrespective of what materials you are looking at, and there are so many of them here, all their properties can be described by one family of equations, which is based on reduced pressure and reduced temperature. So that's what we have here. The same picture on another scale. Okay, this is the same data, but now what has been done is a curve fit was done to that data, and the model is called the Lee-Kessler simple fluid compressibility chart. So there's a Lee-Kessler equation of state, which was based on the data fit. And once we have got an equation, we can put as many points as we want and generate nice continuous curves. And that is what you see on this picture here. So the x-axis is reduced pressure on the logarithmic scale, 0.01, 0.11, 10. And on the y-axis is the compressibility factor from 0 to 1, and actually going up to 1.3 over there. And for all substances, the critical value of the compressibility factor turns out to be 0.29. And here are the curves. The topmost curve, which is very close, this is the line z equal to 1. This is the one. So if we are close to this line, ideal gas behavior is pretty much good. And so let's look at this first line here. Reduced temperature is 5. And what we see is this line goes up there, and you stay very close to 1, almost all the way through, and then slightly goes up, and then after this, the diagram is not given, but they all rise very sharply after this. So at reduced temperature of 5, that means 5 times greater than the critical temperature, at up to, like for this case, reduced pressure up to 1, that means you are pretty close to the critical pressure, the compressibility factor is very close to unity. And that's quite a nice thing to know. But what if you are at not that high a temperature? So that's the next line. Here you see reduced temperature equal to 2, and the line comes like this. Now it is pretty much close to 1 up to this point, which is reduced pressure 0.1. After that it decreases, reaches the minimum, and then again goes up. And then there is a big change between 2 and 1. This is 1.05, 1.1, 1.2, 1.3, and 1.5. At reduced temperature 1.5, again all the curves start here, but at 1.5 it goes down there and then again rises up there. So now the deviation, if you see here, this is about 0.8, Z 0.8. So you are 20% off from what ideal gas equation tells us, and for most calculations that is not acceptable. We want to be within maybe 1%, 2% of the true value. We can never be exact. That's the real world. Then there is 1.2. It dips, the minimum here dips further down. We are down very close, just about 0.5, 0.55, something like 0.53, something here. So it stays below at 1, about 0.1, and then drops very drastically, and then with pressure increases a lot and again goes up there. And at 1 it comes down there and then goes up. So if you look at this part, they all start converging towards 1. So if you go to even lower reduced pressures, all these curves will come very close to 1. And that tells us that as long as you have a vapor, then if reduced pressures are less than 0.1, then at any reduced temperature, the substance will behave like an ideal gas. That's one nice criteria to have. And the second criteria is that if TR is relatively high, between 2 and 5, say like that, then even at reduced pressures up to almost like maybe 1 or even maybe 2, we can say that there is ideal gas behavior at these temperatures. So there are two things that emerge here, that we have two nice conditions, that reduced pressure less than 0.1 and definitely less than 0.01, any reduced temperature, the vapor phase will behave like an ideal gas. The liquid phase will of course not be anywhere like an ideal gas. So what you are seeing here below is this line, which is the saturated liquid state. So as I mentioned, any pressure and temperature we can always calculate the specific volume. But the real specific volume in the liquid is going to be several orders of magnitude different from that, and so you see compressibility factors of point all below 0.1, 0.1, 0.2, something like that. And these are lines of constant dryness fraction, constant Z, 0.7, 0.8, 0.85, 0.9. Not constant, this reduced temperature is constant. And because the saturated state at this reduced pressure and this reduced temperature, many states are possible. The saturated liquid state is a very poor behavior, has very poor behavior like an ideal gas. It's not an ideal gas at all. Whereas the saturated vapor state is getting close to ideal gas, but within still about like 0.95. So this is about 5% off. But if you come further down, then this difference goes down, and at such low pressures, even the saturated vapor, which is what they call here saturated gas, can be reasonably approximated as an ideal gas. So very low pressures, this would behave like an ideal gas, but not at higher pressures. So this is what this picture tells us in a thing. And yesterday when we were looking at many of the property charts, let's go back and see what would happen to the TS diagram. This is temperature and specific entropy there. And we had talked about in all cases that if we are dealing with a substance or a system or a problem in which there is vapor-like behavior, when we make a property diagram, we must always show the dome. And that's what I'm going to do now, is that on this case, let's say that the dome looks like this. That's the critical point. This is the dry saturated vapor, this is the saturated liquid. And what that compressibility chart just told us is that if you look at constant pressure lines that we had discussed earlier, they'll go off like this, but they're definitely not linear though. That difference here is not the same as this. This is going in a very non-linear fashion. These lines are going up like this, the critical pressure isobar goes like this, and they go up like that. So what compressibility chart told us, that if you are far away from this, that means if you are somewhere here, reduced temperatures are very high, that means this is there and you are much above that. And at low reduced pressures, so remember this is increasing pressure. Okay, so this is increasing pressure. This could be 0.01 megapascal, 1 megapascal, this is 220 megapascal, 300, 400 megapascal. So at low reduced pressures and high temperatures means we are somewhere in this region over here. Something like this. And that's where we say that ideal gas behavior is good. And it also told us that even pressures are very low, then you could even get down in this region and say that in some cases this would also be a reasonably okay type of an ideal gas behavior. So this region and far away from this would qualify for classification as an ideal gas. And so if I have to now shrink this diagram and say, well, where are we dealing with, say in the case of air, where we are looking at many processes, say diesel engine, petrol engine, things like that. This is S, this is T, and for things like nitrogen, oxygen, the saturation dome would be somewhere over there. This temperature being like 120 Kelvin, 150 Kelvin, something like that. And ambient temperature is 300 Kelvin, which means we are in this air that we have around us. Reduced temperature is 2 or of that order, like 2, 2.2 or something more. So we are quite high on that. And if you look at pressures here are low. So we are far away. If you look at the constant pressure line over there, these lines would go off there. Ambient air would be, temperature would be somewhere there. So we are looking at this part. And if you look at any process where we heat the air, like say burning fuel in a boiler or in a diesel engine or a petrol engine or in a furnace or compression, in all those cases, temperatures would further rise. So you could say that from 300 Kelvin, we might be going up to as much as 1000 Kelvin. So that would be a line somewhere over there. And pressures, ambient pressure would be say one could be say there, and maximum pressures we deal with many of these applications would be something like that. So we are dealing with a region where many of our applications lie in this zone. And that's nice to know that at the extremes of this, if we check what is the value of z in each one of them, then it turns out that if all of this z is very close to 1, it means that any state inside this can be assumed to be an ideal gas state, and any process that happens in this region, for example, say there's a constant pressure heating which is like this, or constant temperature or constant isentropic expansion which would be like this, say a turbine, gas turbine, aircraft engine, or a compressor which is working, so that would be something like this. So throughout this process, at any instant, Z is equal to 1, which means that throughout the process, ideal gas behavior is fine. And that means that we can do complete analysis of this by just going back to PV is equal to RT. And that's what we do in the first course like this on thermodynamics, that when we look at analysis of cycles like these, we will treat them as ideal gas cycles, use equation of state PV equal to RT, life becomes much more easier, and very quickly we can get a lot of insights into how these systems operate. At a more advanced level, when we go into detailed engineering of these, we will start relaxing this thing and do many more things to it and get this to be much more realistic. But the first cut analysis that we are looking at is good enough to know what the cycle is and what the basic features are, so that is not going to change. So what does this tell us? That if your cycle is in this region, this part is irrelevant. So what we will be doing now is that whenever we look at a problem in which we say that the substance is always an ideal gas, and we are going to plot the processes and states on a TS diagram, we will not show the saturation dome. So in the diagram, if it is not there and we show a bunch of states like that over there, say, or there, we are implicitly saying that this is an ideal gas state. So if the dome is not there, implies this is a problem involving ideal gas. And if you have a problem where we don't have ideal gas behavior and we want to depict those processes, we must work with this part of the chart, and we have to show the dome as a necessity. So this is a vapor cycle or a vapor process, and far away here is the ideal gas process. And in this course, fortunately for us, these two properties are quite different from one another, and so we don't have to worry too much about it. That does not mean that there are no problems where we have both behaviors coming in at the same time. Take, for instance, air, or say nitrogen, which is cooled to produce liquid nitrogen at constant pressure. So that cooling process will follow like this, go there and end up over there. So it started at ambient conditions behaving as an ideal gas. At some point, it said that, well, now you cannot use the ideal gas equation of state, but I still want to know what is the energy transfer in the process. Well, it means that in this type of a problem, we say that, okay, here there is a line, and that line we decide based on what data we have in the property tables. So this line will be decided by the upper limits of the property tables. We calculate changes in properties, say from here to there or there or there, using the tables data. We calculate change in properties from here to there based on ideal gas equation of state, and the total change in the process will be the sum of change in both these processes. So that's how we will have to handle problems where we know that, okay, somewhere I have ideal gas, somewhere I have a vapor-like behavior or a non-ideal gas behavior, then we must make, just assuming ideal gas all the way through is going to be quite a mistake. Okay, so this is the part of this. And now we ask the question that in the vapor table things, the moment I know the state, from the tables we could get all the other properties. And so if we needed to compare S1, S2, or we needed change in specific enthalpy or change in internal energy or any other property, as long as we had two independent properties at the state, we could go to the tables and pick up all the other properties and then do any calculations we want. So that's how we use the tables and charts. Or these days, use of software that is there. And if you don't have a software, you can go online and there are many free things where you just put properties and you will get all the other properties out. So that is what you do here. Here we have two options. One is, of course, we use ideal gas equation of state. That means there are no tables and no charts, which is okay, doesn't matter. The second is there are some tables, but these are largely for a pressure of 0.1 megapascal. So you can say that air or nitrogen or oxygen at 0.1 megapascal, I want to know the enthalpy change from 100 degrees Celsius to 200 degrees Celsius. One can look up this table and get those data. But that is for 0.1 megapascal. For higher pressures, these tables are of no use. At very low pressures also, we can get some idea from this data, but that's not the best thing to do. So tables are of limited use, and so there are very few tables as far as ideal gas properties go. The best option we have in both cases is that we take the full equation of state, which is a relation between P, V, T, and solve it. That's a much more complicated process. Unless you have to do it, you will do it. Otherwise, we let others do it and we use that formulation for solving our problems. This is what we will do in the tables and charts anyway. That's how these things came about, and so did the software. Here also, we can make tables, but there is no real point because in many cases, this is good enough. So now what we will do is, we say, look, how do I calculate property changes for ideal gases? And we'll concentrate first on change in specific enthalpy, change in specific internal energy, then we look at change in specific entropy, and then we will look at some other. Okay, so the next thing we have to do is we define two properties. The first is constant pressure specific heat. We denote this by Cp, and it's defined as dH by dt at constant pressure. Okay, so that's what we have, and we can also write this if we want as dH is equal to Cp dt for a constant pressure. So if H is only a function of temperature, then we can write this as an exact differential, and that's how we get this. The difficulty is that in the real world, this Cp is a very strong function, and I'll show that data for some substances. So we have two options. Either we assume that this is constant, and in this course we will assume that. But we should remember that that's only an assumption, and the real thing would be that we integrate Cp with T from state 1 to state 2, whatever the temperatures. So if you were to do this part and write the full equation, then this is what we will get. dH equal to Cp dt plus a whole bunch of things here. You don't need to worry about it, but I'm showing you how there's a dependence on temperature, how there's a dependence on pressure. The point to note here is that in the square bracket, we have specific volume temperature at constant pressure. So this entire thing is something that can be evaluated from the PVT relationship or the equation of state. And from there, you can do some differentials on it, put it in there, and we can calculate dH from this. So what we do is, we will say that if we define another sub-category within Cp, which is zero pressure specific heat at constant pressure. Zero pressure means that the pressure is, say, reduced pressure is very much less than 1, or say 1.2. At that low pressures, it is reasonable to assume that it is constant with temperature, and to denote that it is different from Cp, which is in reality a function of temperature, we use a new symbol which is Cp0. Some books write this as Cp0 over there. Both have the same meaning. So we put that and integrate it, and the relation that we will use in this course is now coming up, which is that H2 minus H1 is Cp0 T2 minus T1. A very nice and a simple equation that it is directly related to the temperatures that we are looking at. So that tells us how to evaluate specific enthalpy change between two temperatures. So here, if we needed to know specific enthalpy change from here to here, we just needed the two temperatures, and enthalpy change will be Cp T2 minus T1. And if it was up to the limit to where the tables were, then we could get this number from that equation and the remaining enthalpy change from the tables and add them. The differences are independent of the reference state from which property measurements were beginning. So we are okay with that. So that's one new thing that has come up, the constant pressure specific heat Cp. We'll now look at its counterpart, which is the constant pressure, constant volume specific heat. Or Cv. Cv is defined as du by dt at constant volume. And if we work out the full relation using du is equal to all the expression that we have, we will get this type of a dependence. So basically you are saying that this is a function of only T and V. So we get an equation on this side, this big bracket term, which is like earlier, a function of pressure, temperature only. So an equation of state will enable us to calculate this whole thing. And if we have to get the exact internal energy change, we integrate this whole equation in some sort of an equation like this and then get the answer, knowing well that Cv0, like Cp0, is a function of T. So Cv also is a strong function of temperature. That is long and tedious. We won't do that. We will do what we did before with the specific enthalpy. And we say that Cv0 is dH by dt, and du by dt. And when you take it to the other side, integrate it, we get the next equation that we can use in our analysis, which is that u2 minus u1 is Cv0 T2 minus T. And that's a nice compact equation to use for solving problems. So we got two new properties that came out, the specific Cp and Cv, and a subclassification which is Cp0, Cv0, which are zero pressure properties. And we got now two equations, how to evaluate changes in those properties, and what it tells us is that it is only a function of temperature. The question is, how do I get Cv0 and Cp0? These are standard data that have been measured, and over a range of temperatures, these are given in various tables. So what is done there is that it says that Cp0 for this material is equal to this much for a temperature range from this temperature to this temperature. And it also will tell you that this is good enough within say plus minus 3% or 4%. And that's good enough for our purpose. We will follow this. Where 3% is not acceptable, we have to go for the full equation like this one. So these are available in various books, charts, and even on the web. And we can pick up, knowing the material, whether the temperature is then this, we can get the specific heat there and then use it in a problem solving. So that's half the story done for the ideal gas. Now we ask, how do I calculate entropy change? So this could be a process where there is a, say, irreversibility in a compressor, or there is a heating of a gas taking place, and we want to know what is the entropy change. Enthalpy change we got, now we want to worry about entropy change. So we have two options here. Entropy change can be obtained either from a combination of pressure and temperature, or specific volume and temperature. So we will get two equations, both are identical, and we can use either of them in our problem solving. So what we'll do is, first we will look at Pt, then we will look at Vt. So what we get with this is that TdS, we start with the relation that we already had, this is equal to dH minus VdP. So one of the equations we had derived, the Maxwell's equations as we were talking earlier. And now we do some simplifications on this. They are saying that dH, we have already just seen the definition of specific heat at constant pressure, can be written as Cp0 dt. And since it is an ideal gas, so remember this is now only for an ideal gas, V can be written as RT upon T. And so this gives us an equation which is Cp0 dt minus RT upon T, and there is a T on the left side. If you take it to the other side, we get an equation which says ds is equal to Cp0 dt upon T minus R upon T. And that is can be integrated. And to make life simple, we use Cp0, so this becomes independent of temperature. So when we integrate it, this comes out of the integral, and we do a simple thing from state 1 to state 2, and the answer is, we can just look at it and know that what it looks like. S2 minus S1, this will be integral of 1 to 2 Cp0 dt upon T minus R ln P2 upon P1. This term, there is no problem. It is straightforward. R is constant. We take it out, and that's what we get. And if Cp0 is constant, this final equation becomes Cp0 ln T2 upon T1 minus R ln P2 upon T1. And that is the equation that we have been looking for. We have an option of using some property data where a property called ST0 is listed in the tables, which is zero pressure standard state entropy, defined as T0 to T Cp0 upon T dt. And S2 minus S1 will be then ST2 at the zero state minus ST1 at zero state, and we get the answer. Which means that you take the temperature, look up the table, get the value of this one. Then at this temperature, get this value. Subtract the two, you get S2 minus S1. But the caution is same. This is for 0.1 megapascal and at low pressure zone. So this is a quick way to get numbers. In some cases, these two numbers will be very close to one another. When pressures are very high, this may not be good enough to use. So for our purpose in this course, we expect that we will use this equation. That's good enough. Okay, so this is one thing. So I said that entropy change for the ideal gas can come from two parts, pressure and temperature. So this is pressure here, temperature here. The second formulation is temperature and specific volume, and we will look at that next. So here we have entropy change, but now we use a different equation. TdS is equal to du plus PdV. And here we make the substitutions as before. Du we now know is Cv0 dt, and T is RT upon V, the ideal gas equation of state. Again, this is ideal gas entropy change. And like before, we do that simple calculation, simplification, integration, and you get S2 minus S1 is Cv0 ln T2 by T1 plus R ln V2 by V1. And that's the second equation that we have been looking for. So now what we have got, we know how to evaluate change in specific internal energy for an ideal gas, change in specific enthalpy, and now we have equations for change in specific entropy, and that completes everything that we've been wanting for. So we are in now a good shape that knowing some state points, we can calculate all the other properties even for an ideal gas. We did not use any tables. For the non-ideal gas behavior, we use only tables. For ideal gas, we have these four relationships. Life becomes much easier when we look at all these things. Now I mentioned that Cp is a function of, so let's spend a few minutes looking at this data, which is real data for substances. On the x-axis is temperature in Kelvin, starting from 0, 400, 800, 1200, 1400. On the y-axis, Cp in kilojoules per kg per Kelvin, and starts from 0 and goes up to 18. And what you see on this curve is that there are a lot of curves that are over here, in fact over here, one slightly above that, and this one way above that. That means here is a material whose specific heat is like 14 kilojoules per kg per Kelvin. It can take in a lot of energy for its temperature to rise by 1 degree Celsius. And this substance is hydrogen. So that's what we have. A very common substance. We can happily produce it by electrolyzing water, and it has this wonderful property of a very large specific heat. So where does this come in use? That if you want to cool something, you would like to have a substance which can absorb a lot of energy and its temperature doesn't rise too much. Because otherwise then the differential of temperature between the coolant and the material will decrease and the heat transfer rate will come down using the Newton's law of cooling, and that's not a very nice thing. So here is hydrogen, which has a tremendous specific heat, and that's why in large electric power generators in all power stations, whether nuclear or coal-fired or oil-fired, the cooling of the generator, which is like cooling an electric motor, which is generating heat because of I square R losses, that cooling is done by hydrogen. So all these big machines are filled with hydrogen to like 3 bar pressure, 4 bar pressure, and that is the reason why we use such a chemical, which actually is, from a safety viewpoint, is somewhat dangerous, but it's got excellent thermal properties. So this is way outlier. Hydrogen is way out on this chart. So let's now move on from there and look at the next big chart that comes up way up here, and this is helium. So here is helium. Okay, so here is helium, and by looking at it, it looks like this line is almost straight, and that is the case. But as far as value goes, it is 5 point something, which is again a very high specific heat. So helium has nice high specific heat and is completely independent of temperature. That's what we see from this part. Now let's go down further in this. With the last line here, this also looks pretty much straight. And if you see what this is argon. So argon specific heat doesn't change with temperature. Helium specific heat doesn't change with temperature. And you can extend that and come up with the thing that helium and argon are monoatomic gases. They have very little manners in which they can absorb energy in the atom, and so the specific heat doesn't change much with temperature. So these are two monoatomic gases. The dependence on temperature is very weak. Now let's look at all the other things that are lying in between here. We then have nitrogen there. You can see this nitrogen, the specific heat increases slightly as you go up. There is oxygen, which is the cross. You can see this is going up there. So what has happened now is that these are diatomic gases. They have vibrational modes of storing in energy, and so their specific heat is now dependent on temperature much more strongly, whereas monoatomic gases had nothing. Hydrogen was also a diatomic gas, so there is a slight increase we see there. So monoatomic gases, specific heat don't change much with temperature. Diatomic gases, somewhat strong dependence. And you go to bigger molecules, carbon dioxide and water, and this is a propane and R134A, which is a little bigger molecule, and you can see that they all have a dependence on, but qualitatively if you see, their specific heats, including that of water and even nitrogen and oxygen, are way below hydrogen, way below helium, and way below hydrogen. So there's a huge difference there. And this curve, which is, you can see this is for water, this is going up, and we can see that water in a liquid state that we know has a specific heat of about 4.18 kilojoules per kg Kelvin. And we know that water is one of the materials which has the highest specific heat amongst all known materials. That's another way why water is a good thing. Is first, it is abundant, and second, it is good for cooling. So water is 4 kilojoules per kg Kelvin, very good high specific heat. Metals, the specific heats are much lower, but when it comes to other substances, you have helium and hydrogen as two materials with very, very high, and this is good for engineers, whereas hydrogen is dangerous, so you have to be a little more cautious in designing your equipment. Helium is inert, and you can quite happily use helium and not worry about any corrosion or reactions. The trouble is, helium is it's a rare gas, very expensive. You can buy it, yes, but use it only if absolutely you must. So that's what we were looking at, integrating Cp with T. This is the gaseous phase. Okay, now we look at something that you have learned in school days, but it now comes out in 2 minutes by looking at what thermodynamics we have learned, and which is that what is the relation between the two specific heats. Okay, so we have this relation, the definition of specific enthalpy, dH is equal to du plus PdV. True for everything, no issues. Now we say, what about an ideal gas? And we say this dH will become Cp0 dt, du becomes Cv0 dt, and this becomes PdV becomes R dt. And you remove T from there, and you get Cp0 minus Cv0 is equal to R. It's something we have known from school days. Units of all three in SI units are kilojoules per kg per Kelvin. And the second thing, a number that we will now exploit more and more, for gases we do it, that is the ratio of Cp0 to Cv0, which is defined as K, or in some cases gamma, the specific heat ratio. And if you remember your physics from other courses, you find that for air it is 1.4, for monoatomic gases it's about like 1.67, for bigger molecules it is smaller. So that's something that comes up, and this K comes up in many applications that are there. So we have two more relations that we can use, that K defined as the specific heat ratio and Cp minus Cv0 is equal to R. So this came about from a very nice way. From the first law of thermodynamics, we defined this. Ideal gas approximation came this, then comes this. This is always true, but this is the approximate assumption that we made. So this relation is only true for ideal gases and for no other substance. Now we will look at something that we would like to know, is that what if an ideal gas undergoes an isentropic process? So before we go to the mathematics, let's just look at the property diagram and say, well, I'll plot here S and this side is T. We are looking at ideal gas, and now we say, well, what is a isentropic process look like? And it will be a vertical line. So I could have a vertical line that goes like this from state 1 to state 2, or a line that goes from there to there. This is state 1 to state 2. So you can do a very quick application of the equations of the laws that you learned, and you'll find that for this process to happen, W is positive. That means the system does work. It's a work producing device. This could be expansion in a turbine, or expansion in a cylinder piston arrangement, or even, as we saw one more case, zero work but a nozzle. And this could be the opposite, work consuming, like a compressor. So this is like a turbine, or expansion in a cylinder piston arrangement, the power stroke of an engine, or so this is a compressor, or the compression stroke of an, say, a diesel engine or a refrigeration compressor. And the opposite process, this is called a diffuser. So what a nozzle does is that it takes in material at a higher pressure and temperature, and it puts it through a contraction area for one class of flows, and you get a high velocity at the other end. The diffuser just does exactly the opposite. That you put high velocity fluid and you put it through an expanding area. So these are the isentropic processes that we are looking at. And say, well, what else can I know about this for an ideal gas? So what we do is we start with this equation that we just derived, that for this process S2 minus S1 can be written as Cp0 ln T2 by T1 minus R ln P2 by P1. We could have as well used the other equation. There is no problem with that. We could even say that this is Cv0 ln T2 by T1 plus R ln V2 by V1. In the end, the answer will be the same. And we say this is an isentropic process, which means that this has to be set to 0. And remember, isentropic process means that this is a reversible process and adiabatic. Adiabatic means it does not exchange heat during that process. So delta Q or Q dot, whichever way you look at it, is closed or an open system. This is 0, and reversible means it is the most ideal process that is possible. So what we do is we take this equation now, put equal to 0. So it tells us that Cp ln T2 by T1 is equal to R ln P2 by P1, or T2 by T1 to the power Cp, Cp0 is equal to P2 by P1 to the power R, and we can now exploit and apply the equation of state PV is equal to RT, and when you do that and simplify this, you get a very familiar type of an equation, PV to the power K is equal to a constant. So that's something we knew, but now we know very well that this is applicable under what conditions, and only under those conditions. This is for only an ideal gas, for an isentropic process that is reversible and adiabatic. So this has to be applied to any of these types of processes, a turbine or an expansion in a cylinder or a nozzle, and this has to be applied to a compression stroke or a compressor or a diffuser. There can be no heat transfer in the process. If that is the case, this equation is not applicable. So this is one nice important thing that has come out from everything that we have done. And we started off, if you look at the origins of where it came from this equation. Where did this come from? We got the definition of specific enthalpy, which came from the first law of thermodynamics. Then we exploited the second law of thermodynamics. Okay, so PV to the power K equal to constant. And now we say that what if the process is not like this? Some irreversibilities are there in this process. Or what if there is heat transfer during this? Can I use this equation? The answer is no. So what is the next best simple thing that one can do? Well, we can make an approximation. And we say that instead of calling PV to the power K equal to constant, I will call it PV to the power N equal to constant, and use it with a fair degree of caution. This could be a closed system undergoing this process, or it could be a flow going through a passage or through a turbine or through a compressor and doing this. As long as we know that at any point during the process the states are known and those states follow this equation, then we are okay to use this equation. And when we do that, we can then do a lot of other calculations from here. But then remember that N equal to K if and only if it is an isentropic process. Under no condition can we use that. The treatment of both follows very similar to one another. So we will look at some more examples of how we use this, especially in computing work. And for work, we will look at two conditions. On one side, we will look at a closed system, and then we look at an open, means it's a flow process. So let's see what happens in a closed system. So that's a device in which there is a cylinder and a piston, and we apply this force to say compress this system, the substance inside this. Or alternately, we allow this to expand and do work against a resisting force, so we get work from. And for a very small change of volume, say from there to there, dV, we assume that the pressure acting on this for an infinitesimal change in volume is constant at P. Then the work done by this will be that if this was the displacement delta L or dl, then the force being applied will be P into the area of this device, this area, and the work it will do, elemental work for that, say delta W, this will be PA into dl, and that's where we say this is P times dV, these two terms. So we say that for a very short period of time, the pressure did not change, and for that little part, the work done is this much. One actually does these things these days with numerical simulations, and let's look at a graph. We say that if I know that this is my specific volume and this is pressure, and we were say expanding and coming to these states, and I want to calculate the work, somebody would say, oh, fit a curve to this, get the value of n and then do something. But there's a second way to do it, that we say that this pressure was there for a small period of volume, this pressure prevailed for this volume change, this pressure prevailed for this volume change, this pressure prevailed for this volume change, and so we do something which we learned in mathematics, which is we do numerical integration. And that's what one does in the laboratory. When you're getting the efficiency of, say, a compressor or an engine and looking at what happens in a compression stroke, the instruments give you this type of a discrete data. It's not a continuous data. And one then does this type of a calculation to calculate the work done or the work done by the system or work done on the system. So it's PD. And now we say that initial position was 1 over here, final position is 2. How much was the work done by this process? And all we do is we integrate this and say that W1 to 2, because this is now a closed system, this is equal to integral 1 to 2 PdV. We are only exploiting the definition of work. It has nothing to do with the first law or the second law. It's simple, straightforward definition of what is work. And work as we defined it in thermodynamics. So when you do this integration and assume that this is an ideal gas undergoing isentropic, when you put all of these things together, then this W1 to 2 comes out to be P2 V2 minus P1 V1 upon 1 minus A. So that's something you saw in school and we kept using it. Now we know that what all things that we have gone through it to get to this point. And that's the important thing to remember, that this is an idealization of this particular case. Sorry, 1 minus K. And if it was following N, and that is what is a polytropic process, then this work becomes P2 V2 minus P1 V1 upon 1 minus. Now what it tells us is that when K is always greater than 1, negative work means work done on the system, a positive value means work done by the system on the surroundings. Out here, this N can take any value. There is no restriction on this. In relation to K, it could be between, say, 1 and K or more than K. All you do is ask, what is it that would be necessary to produce that type of a K. If N is between 1 and K, this would mean that it is a reversible process or there is heat transfer out of the system. If in that work expansion process you also heat it up, you may get N more than K. And if N is equal to 1, you get it is an isothermal process. In which case, this definition gets into a problem because the denominator becomes 0. We have to go back here and say that now PV is equal to RT, and from there we start integrating it and you get a slightly different form of this, which is a logarithmic function. So I'll leave it to you to do that derivation. So that is the interpretation of this value n. Usually in real cases, when there is some irreversibility, and also in all practical cases, there is some heat loss to the walls of the cylinder, or we are deliberately cooling it, like in an internal combustion engine, n will be less than k, and then you can see from here the work done is different from what we had earlier, it will be slightly less. And if you want to plot those cases on this property diagram, then we say that if it was operating between the same pressures, which are these two pressures, this is P1, this is P2 isobars, the real process in this case will go like that. You will always have increase of it. And in this case, where these are the two constant pressure lines, the real process will go like this. So this is 2 isentropic, this is 2, this is 2 isentropic, this is the real. We will see increase in entropy during these real processes. Okay. So that's one thing to remember. Now we come, that was for a closed system, this equation. Now let's see what happens to an open system. So in the open system, we had that for all the assumptions that we made, steady state, delta KE, delta PE both being 0, one inlet, one outlet, and for the timing we also assume that it is adiabatic and reversible, which is what we are looking at the isentropic process. Then we can derive this equation and say that dH is equal to VdP. So you check, you can check yourself if this is VdP or minus VdP. And now we integrate this, assuming ideal gas equation of state. dH is this, and we use the ideal gas equation of state, do the integration 1 to 2, and this is now integral VdP 1 to 2, and we get a very different type of a function, which is n or k upon 1 minus k PE small volume minus Ti. This is a very different looking relation than what we had 2 minutes back. For a closed system, the work done was P2V2 minus P1V1 upon 1 minus K. Or P2 PV can be written as RT, so this can also be as RT2 minus T1. In the case of a flow process, this is K upon 1 minus K, PE VE minus PI VI. Again, we can put this as the equation of state and get RT TE minus TI. But now it is K over 1 minus K instead of 1 minus. So this is something we need to be careful about, that open systems, the relation is this, and what is this? This is W dot CV. That is specific work. Sorry, yeah, because this kilojoules per kg of the working substance. So this is the actual work, W. This is specific work, and it tells us that if you want double the work, you can double the mass flow rate, your work doubles. You want triple it, triple the mass flow rate, work triples. And that's how we actually scale up and design machine. And the same thing one can do and see what happens when it is a polytropic process. And instead of K, we just get substituted by N. Now let's look at something where there's a little bit of doubt as to what is actually going on. And what I have in mind is a cylinder piston arrangement into which we introduced, which is filled with, say, dry saturated steam. And when this was allowed to expand, we know that on the TS diagram, now I have to show the thing because I'm talking saturated, so the dome has to come. This was the inlet state, and if this was isentropic expansion, which is the work producing device, the final state will go like that. It becomes wet. But then as a first approximation, if we know these values here, we can approximate this process with some value of n and still consider this process as PV to the power n equal to constant. Even though this was not an ideal gas. But one has to be clear that we cannot exactly tell using this equation what were the intermediate states. It is only an approximation of what the real thing. So that was a fairly commonly encountered relation for ideal gases, where we do adiabatic expansion or compression. If we do heating or cooling, we already got those relations. Change in internal energy was Cv0, T2 minus T1, and change in enthalpy for flow processes was Cp0, H2 minus H1. Okay, now we'll define, so we have come to the conclusion of what we have been looking at, that we now have all the properties and the change in the properties. So we have defined many properties, and we got change in properties for both vapor-like behavior and ideal gas. And that's what we were looking for. So what we can do now is use this data to go back to those equations that we wrote in the second module after the analysis of the laws. And now we are in a position to put numbers in there and start getting the answer. So this last part, as you see in the total problem solving process, is only one small little thing. The initial part where we formulated the problem, did the approximations and got the equations that we want to solve. If we made a mistake at that point anywhere, the next point where we put numbers into the equation doesn't really help us. So we have to be very clear on that part. After we are done with that, we say, well, okay, now let me put numbers wherever they come from. What I will do to complete the discussion on properties is to introduce two new properties. You might have come across these in physics or chemistry courses. One is called the Gibbs energy, and the other is the Helmholtz energy. Sometimes this is referred to as Gibbs free energy. Sometimes this is referred to by some as Helmholtz free energy. And in some text you will find this referred to as Helmholtz function. Gibbs energy is denoted by G. The specific Gibbs energy is small g. Helmholtz, we will use symbols A, but in some books you will find the symbol psi has also been used. We will use A for capital A for total Helmholtz energy, small a for, and these definitions complete the set of properties that we would like to have for a pure substance. The Helmholtz energy actually is much more attractive because it is from here that we develop that equation for a PVT curve, and then by using property differentials we calculate all the other properties of a pure. We do not need to go very deep into this, but one should be aware that this is the totality of properties that we are working with. So for completing the discussion's sake, I am showing you. So Gibbs energy is defined as H minus Ts, or G is equal to small h minus Ts, and Helmholtz energy is A is equal to U minus Ts, or small a is specific internal energy minus Ts. So what we have done something is, in both cases we have somehow got something less than Ts. And this becomes important when we look at what is called the work potential of a reaction, or work potential of a change of state. And this tells us what is the maximum possible work that we can get. In the case like a fuel cell or a battery, that's where this property comes in. This property also comes very important in looking at reactions, where we ask, if I burn the fuel in air, what is the species that I will get, what is the temperatures I will get, and there is the Gibbs energy which will tell you what is the final composition of that. This is also good for mixtures, and say, look, if I mix so much water with so much air, what is the pressure and temperature that I get? It's the Gibbs energy that helps us to get that answer. Okay, so these are the two energy functions that are there, and now which summarizes all these properties that we have looked at. This is there in the notes. We don't need to really memorize or go deep into this, but it is good to know that all these things are there and they have an importance in thermodynamics. So here is a table. There is a property, here is Maxwell's relations, interpretation of that property, and what functions came out of this property. So on this side we start with U. U is saying the function of entropy and this, because du is TdS minus PdV, which means that U is the function of S and V. So that is U equal to USV. And by doing a little bit of small differentials, which I have given in the notes, which I'll put it up very soon, you get dt dv, and there's a bracket missing there, is equal to minus dp ds at constant volume. And you also get from there that temperature is du ds at constant volume and pressure is minus du dv at constant entropy. So that's what we begin to see, that how all these properties are related to each other by very nice mathematical functions. So if only we have a PVT diagram which satisfies all these things, just differentiation is good enough to get all the other answers. Okay, so this tells you that this is the internal energy of the molecule, that includes its vibrational energy, translation energy, rotational energy, electrical energy, and any other types of internal energy that a molecule may have. That's all there inside this. To that we added PV, which we called as the flow work, as H equal to U plus PV, and we got this equation dH equal to TdS plus VdP, and that gave us the expression that dt dps is equal to dV dsP. Our temperature is dH ds at P and V is dH dP at constant entropy. And by looking at given energy, it's the maximum work that is possible from a process. G equal to H minus Ts, dG equal to minus ds dt plus VdP, and again we get these two differential equations. Our specific volume is dG by dP at T, and S is minus dG dt at T. And the last one is of the Helmholtz energy, A equal to U minus Ts, dA is minus ds dt minus PdV, and you get these two differential equations. And pressure is minus dA dV at constant temperature, S is minus dA dt at constant specific volume. I have listed here 4 more equations which are useful, and these are the equations that we start using to get from PVT diagram all the other properties that we are looking for. And the nice thing about using such a formulation is that if we have the right formulation, just a few sets of differentials and we get all the answers. There is no approximation involved, and this process is superior to saying that I take data and I do a polynomial fit. Polynomials are very badly ill-behaved between data points, and differentiating them could give serious mistakes. So we be very, very careful that if you are working with polynomials, whether it is for properties or any other case, differentiation is very, very dicey. Okay, how we got those equations? So this is one little thing. Du is TdS minus PdV. U is a function of S and V, and we just differentiate it to get this part, and then we can put various other substitutions and you get this big equation. Don't worry what is there inside this, but we'll just see what it means. That if I want to evaluate U, I need CV0 as a function of T, and I can integrate it with temperature. I have this big expression which is what rho, P and T. Rho, P and T. So if I have an equation for the PVT relationship, I can put that and integrate with respect to rho, and this is some constant which is somewhat arbitrary. We can pick what we want. So that's how we do all these operations, and we get U. And similarly, there's a second function, how we get S from PVT data, just to know that such a method is there. S can be written from TdS equal to du plus PdV. We substituted that, then we did some more substitutions, and this we get that S is a function of CV0 as a function of T. That's what you need here. This is R ln rho. Rho is the density. We need density there. And this whole thing is an integration of density where you have rho and dP dt coming in over there. And then this one is a constant, depending on where the reference state is there. So what these two equations showed us is that if you have a functional relationship between P and T and rho, so P as a function of T and V, or P as a function of T rho, then we can differentiate it, put it in this equation, and evaluate entropy change. And this is valid for every state. There is no approximation here because we are looking at a PVT relationship, or this relationship that we have, which is good for all states. So we don't have to depend on somebody giving us the charts and the properties and the number. We have a little bit of entrepreneurship. We can make these charts ourselves. Okay, so that is two of the properties. And now I'll just give you some examples of how we get this P rho RT type of a thing. And what we have done is P equal to rho RT, which is the ideal gas equation of state. And we added to this big term here, and then which is Ci, which is some sort of a constant as a function of temperature, and another function which is of density. So we've done a separation of variables of sorts, and this is where, if you look up mathematics, you would have come across the Helmholtz partition function. And that is what we have done here. And then we do curve fitting and get values of Ci and Hi, which will be many, many constants. So I'll just show you equation of state which fits all the data. It is not that there is only one equation which we can use for fitting all this data. We see here, this is the first equation, P equal to RT upon V, and then a whole bunch of things put in there, which are only functions of temperature and density, explicitly. Another formulation, P equal to rho RT plus a whole bunch of other things. Some sort of a variable coefficients coming in. Then P equal to rho RT plus some other form of these. Another formulation is got a whole bunch of other things. 28, 32 constants coming in over there. So that's okay. And the reason we put these is that for some materials, some equation fits best. For some other materials, some other equation fits best. So like this, we have many other equations coming in here. And the equation that is of use to us for water is this equation, P equal to rho RT multiplied by this thing. Q is a partition function which is given by this, which has got so many constants in it, or by this. This is the one used for water. So you get this big long equation which has got lots of constants which are given separately, and from there we can then put it into this equation, differentiate it as much as we want, and compute any properties that we want. So we can make our own program and say that, look, I can do this. But the trouble is, the two independent variables in all these formulations are pressure. So if we know a state where pressure and enthalpy are known, then direct use of this equation is not possible. We have to develop some other techniques of interpolation and some approximation to get to the correct answer. Most of the web-based programs or others that you see may not have that flexibility, that if I specify specific enthalpy and specific entropy, what is the pressure and temperature? That question most of these programs will not be able to answer. Okay, so those are the type of equations we have. These are equations for CV0, constant volume specific heat that we were talking of. Depending on the materials, we have various types of things which have varying degrees of dependence on temperature. That's all. There is constants and temperature to various powers, T square, T cube, T to the power 4. Like that. The saturation pressure curves that we drew yesterday, they can be expressed by any of these type of equation. Ln P is equal to some function plus function 1 by T, ln T, and things like that. Or P by Pc is a function of temperature. And so this is a 1:1 equation. You specify the temperature, you know the saturation pressure. There are many other formulations that are possible. Again, some are good for some substances, some are not good for. This is a formulation for saturated liquid density. The density of the saturated liquid state, rho F, or specific volume Vf. This is given as a function of this, which is only as a function of temperature. So you know the temperature, we know rho F. We can make similar things for rho G also. For every material, say refrigerant 14, I'm showing you the example. The critical constants are known, Tc, Pc, rho C. The reference temperature is given T0 as 125 Kelvin, molecular weight 88.01, and the constants that are used in the equation, it tells you which is the equation that we use from those, and what are the constants to be used for that. What for saturation pressure, which is the equation and what are the constants. And like that we can put all these together and produce all those property tables and charts that we like to use. For water, that's the type of formulations you see. The same equation I showed you. There's so many constants that we need even for the P rho T equation, which is Q and P6. Saturation equation has about 10 constants. Rho F has 8, CV has. So that's the general way in which people have developed all these properties, and we have the benefit of using all of that in the problems that we have solved. The last thing is how we get the compressibility. PV equal to RT got modified, and you have come across some of these in your other courses. There are different types of equations of state. Starting here from the top left, First one is Van der Waals equation of state. You might be familiar with that. And this is P equal to RT over V minus B minus A over V square. The form that it took was that under some conditions the material is denser, in some cases it is less dense depending on the pressure and temperature. So these two terms take care of those physical phenomena of gravitational attraction and nuclear repulsion between them. Doesn't fit very well, the first equation. Then came the virial equation where Z equal to PV equal to RT was defined as a function of V temperature and specific volume square, specific volume Q. So it works a little better and gives you the value of Z. Then the BT Bridgman equation of state, RT upon V bar plus various constants with V bar, V square, V cube, V4. This is specific volume. Then the Benedict-Webb-Rubin equation, it gets a little more complicated, but same thing, that RT upon V plus some constant into RT plus a whole bunch of constants and combinations of temperature and specific volume. That's the common feature in all of these. V Kessler, a little more simpler, 1 plus Bt upon specific volume square, cube, fifth power, square power with T cube, and like that. The cubic equation of state, Redlich-Kwong equation of state, and so forth, depending on what one is interested in. And so you are only interested in looking at the vapor phase of a refrigerant in a compressor or in an air conditioning system, then you can say, look, this equation is good enough for me. I am not too worried about what the equation of state for the liquid thing. From there, I'll get some simple state, and from there, I'll pick up all my values. On the liquid state, I'll just say H is equal to Cp dt and get my data from there. So one can do a mix and match of some properties from here, some properties from there, and solve the problem. In our case, we won't go into those details. We'll just stick either with the ideal gas solution. Okay, so that's basically brings us to the end of our discussions. We'll take questions and then I will summarize what we have done. Okay, the first question is it possible for polytropic process to occur naturally? And the answer is yes. Say air flowing through a building, or at some point there is a contraction and air goes through it, the velocity goes up. And even though we assume temperature to be constant, we can, the thermodynamics of this, that we can approximate that as PV to the power n equal to constant. If you mean that naturally that you leave something to itself and it will do it, that's also possible. You take say a shock absorber and you compress it and let it go. As it comes out by itself, it could follow that sort of a thing. Especially a gas-filled shock absorber. That's what it will do. So it is possible that because those processes are irreversible, that's why it is not PV to the power k equal to constant. The irreversibility will make it n, even if that device was adiabatic. If it is reversible and adiabatic, then the exponent is k. But if it is irreversible, internal irreversibility is in the device and adiabatic, then this will be n, and typically this will be slightly less than. If you are cooling it, then of course n will come down even more. And so all things like engines and compressors and things like that, n is less than k, which if you do a complete analysis will show you is not a very good thing, because that's not the best efficiency, best way to do that compression. People would try to make things that we would like to make it as adiabatic as possible. And a lot of work has gone on in saying, can I make an internal combustion engine where the cylinder piston arrangement is adiabatic? Right now it is not. When you look at a motorcycle engine, it has got fins on it, so whatever heat was there generated by the burning of the fuel, some of that was conducted to the atmosphere through the piston and the fins, and the rest of it, you got some work out of it. So by burning fuel, you lost some energy to the atmosphere, and that was not the best thing to do. So I make it adiabatic by putting a lot of insulation on it, fine, but then the material will run much hotter. It will get very hot, and materials like aluminum or aluminum alloys may not be able to withstand that type of a temperature. They may lose their strength, their properties, their wear and tear may happen, the lubricating oils may get burnt up or destroyed, and so the engine may not be very a long-lasting engine. But that is definitely a thermodynamic basis and the reason why you would like to make such a process adiabatic. Okay, then what I will do is, if you have questions, please do ask, or you can post it on the forum. Let's see what we have learned and where have we reached in this course so far. Okay, could you please explain the importance of Gibbs energy? Okay, I have deliberately not gone too much into detail on that, but Gibbs energy basically tells you that, for instance, in a chemical reaction, we know that we get so much heat out of it. question is, if instead of the chemical reaction happening and instead of taking it out as heat, what if is it possible that what the work I can get out of it? And that is what Gibbs free energy tells us, that that is the maximum work that we can get from a particular process. In the case of non-reacting systems, it has got a slightly different connotation, but it essentially is still saying that it is the maximum work that you can get without say interaction with the surroundings. That's very roughly what Gibbs free energy is about. Okay, so what we have done in this course, we have 3 modules so far, and now we have covered all the knowledge that we want to solve a problem. We have everything. Whichever problem, whatever way it is, now that is not an issue for us. We know how to do a first cut analysis of all these type of problems. In the first one, we said we have to worry about concepts and definitions. In the second, we said what are the laws. And what we learned was universally true. There was no ifs and buts. It did not depend on the application. It did not depend on the examples. And now we looked at to do calculations of changes in properties. We have learned how we can compute and calculate the properties of a pure substance. So all of these together now give us the confidence that we can completely solve a problem and answer various questions. So let's take a couple of examples. We say that we have a cylinder piston arrangement in which the piston moves from this position to this position. These are stage 1 and stage 2. There is some material, some substance in it. And during this process, certain amount of heat was given to it. And we want to calculate what is the work done by the device. So we know now, we start off the way we did in the beginning, that we identify the system boundary is what we draw first, and say whether it is an open system or a closed system. And we say this is a closed system, so the way the equations will be that mass of what is there inside this is constant. That means mass in state 1 is equal to mass in state 2, conservation of mass. And the first law tells us that Q12 is equal to W12 plus E2 minus E1. And then we make some assumptions of delta KE, delta PE being 0. And that comes that Q12 is equal to W12 plus U2 minus U1. So we need to calculate various things, and we then write down what is it that is given in the problem. Say state 1 is fully defined, that P1 is given and V1 is given, and say mass could be given, which means that specific volume at the beginning is known. And we said state 1, I have 2 independent properties, I can get enthalpy, entropy, everything else that I want. And now it depends what's with state 2. We know that if it went up there, the mass was the same, M1 equal to M2, the volume increased by doubled or tripled or quadrupled, whatever, specific volume change we know, but say we don't know what the final pressure is. If we are given the final pressure, P2, then we say that, well, now I know both things, or say T2, and we know that state 2 is defined. We can get U1, U2, and if heat transfer during the process was known, the work for this process can be calculated. And what one does then is that at this point, what we had not done so far in our problem solving was saying what is the substance. Having learned the properties of your substance, we now have to make a decision. Should I assume this to be a vapor and go to the tables and charts, or should I assume this to be an ideal gas and use PV equal to R? This is an important decision we have to make. And for that, we need to look at the problem and say, well, what is it that is given here? This could be superheated vapor, in which case your first idea should be that, look, I must treat it as a vapor. Let me not assume a priori that this is a gas. At the end, I will check again if it is a gas, that's good enough, or if I don't have enough other information, I may assume this to be a gas and find out what. So this is the next decision we make, that if I need to get the properties, do I have to have a vapor or an ideal gas? And from there we get the equation of state, and from here we go to the charts and get property data from there. And then we put it in this, go back, calculate what is U. If it was from the vapor charts, this U will be computed by looking values from the tables. If it is an ideal gas, we would put U2 minus U1 as CV0 T2 minus T1. Or from the charts, we directly read out the two values, and if values of U are not given, we would definitely have values of H which would have been given. So we can get H2 and H1 from the charts, P1, V1, P2, V2 are known, and from there we can get U2 and U1 and substitute in this equation. And then we do the remaining calculation. So this is the additional thing we have put, and in doing that, we are now actually putting numbers on all of these. And that is where we are getting quantitative and getting numbers. So we did not do that at the end of module 2. We just said that I knew the property and we gave some arbitrary symbol to that property. Now what we will do is go back and put numbers on that property, put a title or a name on the substance and solve those problems. So that's what we will do now. We can also use these properties to do various checks and balances and say, take an open system. And so somebody says that I have made an adiabatic plus reversible turbine that can expand from P1 T1 state to P2 T2 state and produce this much amount of work, or this, or W. And the first question we ask, is such a machine possible? So what we do, we go back and say, look, this is a turbine that we are talking of. So that's this picture. There is the substance going in, the substance coming out, and there's some work coming out. There could be some heat, but if it is adiabatic, this Q dot CV, this is equal to 0. And all we are left is W dot CV. And now say, well, the problem will tell you that gas expands in a turbine, and that automatically tells you that word gas, that you can take it to be an ideal gas. Or if we say it is steam expands in a turbine, then by default we presume it is not an ideal gas. So that question will get answered, vapor or ideal gas. And then we draw the process on a property chart and say, well, this is state 1, they have given this, and this is a state 2, or maybe state 2 could be there, or state 2 could be there. We don't know. And if we plot it, we can very quickly see one thing, that if on this plot, this exit state, so this is the isentropic case. If the final state is to the right of this, the turbine is possible. If the final state is to the left of this and it is adiabatic, the turbine is not possible. So what we have done is we went and said, well, I will calculate S1, we will calculate S2 and ask, is S2 greater than S1 or equal to S1? If yes, turbine is possible. No, turbine is not possible. The work that is claimed, it may be right by the first law analysis that this work would have been m dot is 1, h2 minus h1. And this came from a series of assumptions that we have run. So this may be true. It is getting that much work. But if S2 is not greater than S1, then even though it satisfies the first law, it says no, this is not possible. You cannot make such a thing. We'll take one more example and then we'll stop. We will look at analysis of a cycle. And what we have learned now is that a Carnot cycle has two isothermal heat transfer and two adiabatic reversible work producing processes. And now we say what constitutes in the real world for a given substance on this TS diagram, where is a Carnot cycle? So what we do is we just say that here is the saturation dome, and we know from what we saw yesterday on the TS diagram that even at very high pressures, this line goes very close to it and it goes like that. That means to the left of this, states are not possible. All the states are to the right of this. And if this is what the Carnot cycle is, what it tells us that any square or a rectangle is a Carnot cycle. If it goes this way, it's a work producing cycle. If it goes the opposite side, it's a heat pump or a refrigerator. So it has 4 states, 1, 2, 3, 4. And we want to know what is the work done per cycle. Well, we need to know what is the different cyclic integral of heat or the cyclic integral of work, and that will be the answer. So a cycle could be there on this property diagram. Now we are putting numbers. Nothing stops us from saying that I have a Carnot cycle sitting over there. Perfectly fine. Somebody says I'll make a Carnot cycle like this. Theoretically, absolutely no problem. Practically, we start seeing some problems. That it is now gone into the wet region, and as work producing or work consuming devices go, so W type devices, turbines, compressors, or anything, there is one fundamental principle of engineering that this will either be a liquid or it will be a completely a vapor or an ideal gas. It will not be a wet state. There are serious engineering issues with this. Why? If you want to make like this or like this, it's a very, very difficult task from an engineering perspective. Thermodynamics says perfectly fine. So you can make a Carnot cycle there. One can even say I'll make a Carnot cycle there or a Carnot cycle over there. But somebody says, well, I'll make a Carnot cycle like this. Theoretically, all of them are possible. The efficiencies, we can see what they are. Practically, if we start putting numbers on it after selecting the material, so we select the working substance and start looking at what numbers start coming out for specific volume, enthalpy changes and things like that, then we will see that there's a big problem. Something is possible, something is not possible. A Carnot cycle far away from this dome, like this one that I have drawn, this is completely an ideal gas thing, quite nice and easy to look at. A cycle which could be like this would also be a Carnot cycle, somewhat possible, but still it has got problems with it. But this will be a vapor thing, this will be only an ideal gas cycle. So when we have 4 such states, how do we do the cycle analysis? And for that we need two independent properties at every point. And let's see what happens in this case. What I'll do is make a little matrix. On this side I'll put the state numbers 1, 2, 3, 4, and this side properties P, T, V, H and S. So how many properties do I need to know to define the Carnot cycle? One is of course T1 and say T4. So I say I have specified this and I have specified T4. And then say the pressure at and the other two states I need something more, and let's take that say that we know the pressure in both cases. Question is, do I have enough information to complete this table, which means that do I have two independent properties at every state? So let's quickly go through this. Say if state 4 is fully defined, then I can compute V, H and S. And I know from this that S4 is equal to S1. So if this is known, then this is known. The two are the same. And then we look at this thing and we say if I know T1, do I know T2? And the answer is yes, this is the same T2. And from here we know that T3 is same as this, so this T is also known. So now we have got two independent, one property at each of these states, and we say, what do I know about 2 and 3? The entropy is the same. So if I get entropy at any one of these, which is, say, if I know one of the properties, then this is there, and then this comes out. And like that, we can complete this table and say that S1 is equal to S4. So at S, this is entropy we have already taken. S2 equal to S3, T4 equal to T3, and T2 equal to T1. And with doing that, you can see that if we get two independent properties at any point, the rest of the entries in this table we can very quickly complete, whether it is a vapor or whether it is an ideal gas. Once we have done that, and maybe we may not need all the properties at all points, say specific volume may not even be needed, then we can go back and calculate all the other things which the law requires us to do, that work is equal to the cyclic integral of heat is this property minus that property minus this property, like that, and we can calculate all of that. So this is one way we can tackle cycles by making a matrix and asking ourselves, in the problem, not necessarily in the numbers but in the words, do I have enough information that I can calculate two properties at every state? If the answer is yes, then it is possible to solve the problem. Then we go ahead and solve it. Here's a question. Okay, what is the question between nozzle and diffuser? Okay, so there are two devices, a nozzle and a diffuser. Now this is a device which accelerates a flow. That means in the direction of flow, the velocity increases, pressure decreases. The diffuser is exactly the opposite. It decelerates the flow. That means in the direction of flow, velocity will decrease and pressure. So if you look at, say, air going through a passage like this, here the pressure is P1, T1, and it goes through this and comes out at a higher velocity. The pressure here has become P2, T2. The velocity here, V2, is much greater, or say greater than 1, and P1 is less than P2. So this is a nozzle. With the one little caution, that those of you who have gone into compressible flow studies, you realize that this is true if everywhere in this, the Mach number is less than 1. It is a subsonic flow. Now if you just reverse everything, we get a diffuser that you send in here at P1, T1 and some velocity V1, and what you get here is P2, which is greater than P1, V2 is less than V1. And where do you see these type of things? If you recall the rocket that I showed you, PSLV being launched, at the bottom of the rocket, you could have seen a structure like this, from which there were gases coming out. This is a diffuser. So we produced high temperature gas, then we accelerated it to make it high velocity by dropping the temperature, and then we got it out here so that the pressure increases and there is pressure acting on this which pushes the rocket up. So diffusers are required in those rockets. Like before, this is also the case here that this will happen if the flow everywhere is subsonic. And the reason for putting this is that if the flow were the other extent, that Mach number is greater than 1, which is the supersonic flow, then exactly the opposite will happen in this passage and opposite will happen in this passage. This will decelerate the flow, this will accelerate the flow. Okay, but that's for a different type and a different course. Right now we are not going into that, so but just for completion of the description of what's a nozzle and a diffuser, I have shown this. In both cases, if there is no other dissipation and there is no heat transfer, ideally both would be isentropic, S equal to constant. If there were irreversibilities, exit entropy will be more than inlet entropy, and on the property diagram, say TS diagram, the nozzle will look like this, ideal nozzle, and the same pressure, a real nozzle will do this. And a diffuser from here, in the ideal diffuser, it will go over there. The real diffuser, this will go there, and this will be the exit state. Okay. So that's what's a nozzle and a diffuser. Any other questions here? Okay, so we will conclude at that point that we have now got all the theory and the property and the laws cleared up. We have already attempted a certain systematic way of solving problems, and in the last module we will come with applications and we will solve some problems during the lectures. If you want some particular problems to be addressed, please post it on the forum. I will address that in the last module. So with that we stop, and thank you.